Hi everyone, welcome to this virtual chemistry lesson on the third type of intramolecular bond, that is covalent bonding. So this will be your homework until the next time we see each other. So let's see here, let's take this up. Alright, covalent bonding, the type of bonding that builds up molecules through shared electrons in covalent bonds. And let's get into how this works. Covalent bonding, it only occurs between nonmetals and nonmetals. So if we look at a molecule, say H2O, water, since it only contains nonmetals, we immediately know that it contains covalent bonding. Remember, if it had been a metal and a nonmetal, we would have had some sort of ionic bond going on. And if it had been metal and metal, then it would have been some sort of metallic bond going on. But for covalent bonding, it only occurs between nonmetals and nonmetals. The difference in electronegativity is below 1.7. Since it's similar compounds, the difference in their electronegativity isn't going to be too large when we're dealing with this type of compounds. Nonmetals share valence electrons with each other without letting go of them. And this is because both nonmetals that form a covalent bond are going to pull on the electrons really hard, not really letting go of any electrons, because they have high electronegativity values, if you recall. And molecules are built up of covalent bonds. For example, here we have ethane. You see it contains hydrogen and carbon, and hydrogen and carbon. There's only these two types of atoms in this molecule. And this molecule, as you can see, is only built up of nonmetals. Remember, hydrogen is an exception and is a nonmetal in the classification we use. So all molecules are built up of nonmetal atoms that are bonded together via covalent bonds. We've been talking about properties of ionic compounds, and we've been talking about properties of metallic compounds. There are some properties specific to molecules, but they vary a lot dependent on the molecule structure and shape, as we will see, for example, when we talk about intermolecular bonding later on. Right, so let's start to talk about a type of covalent bond that you will see throughout the rest of the chemistry course, and that's single bonds. These can form between nonmetals that share each other's electrons, and let's see how this works. On this picture in front of us, we have two fluorine atoms that are going to react and bind to each other, lower their energy, become a little bit more stable anyway. And how can they do that? Oh, how can we know that this is a fluorine atom? Let's count our protons, shall we? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think I should have drawn this correctly. 9 protons, then we know which element it is, right? Atomic number. But say that we have these two atoms that have 7 valence electrons, and they want to lower their energy, so they're going to react with each other. How do they do this? Well, the atom on the left is going to pull on one of the electrons on the atom to the right, and vice versa. So they start pulling on each other's electrons in such a way that their outermost shells overlap, and we get something looking like this. They share 2 electrons, one from each. And if we look at this atom right here, thanks to it gaining an additional electron, it now has 8 valence electrons. It has reached a noble gas structure. If we look at this guy to the left, it also has 8 valence electrons. It has also reached a noble gas configuration. So they're both quite pleased and more stable than they would be if they were just atoms by themselves. So we get a fluorine molecule, which we usually write like this. This lowercase 2 here, subscript 2, indicates that we have 2 of these atoms per unit in each molecule. We can indicate the bond formed between these two atoms in such a molecule with a little line, which indicates a covalent bond. Right. We can also look at the Lewis structure here. Single bonds, very important, single bonds are formed when we have atoms that only share 2 valence electrons between each other. Then we call it a single bond. So a single bond equals 2 shared atoms, and I want you to write that down. If we draw it with a Lewis structure, we can write it like this to show that we'll write them side by side, these 2 electrons, just to show that they're shared. Okay? Here's an alternate model of a covalent single bond. So we have 2 puppies playing tug of war. And at any given point, who is currently having the shoe toy? Well, at this point, at this instance, when this photo was taken, we could say that both of these puppies have this shoe toy. They're both pulling on it, but it remains shared. So that's very similar to when we have 2 atoms pulling on each other's electrons and sharing them. Just a little alternate model there. Okay. Another type of covalent bond that you're supposed to know about is the double bonds. And we're going to introduce that by looking at oxygen. Oxygen, in order for it to reach a noble gas configuration, it requires 2 more valence electrons. Why? Well, let's count the valence electrons. 1, 2, 3, 4, 5, 6. So we have 6 valence electrons here, and we need 8 in order to reach a noble gas configuration, because this is a non-metal and it's going to take up more electrons. So let's see what happens when we have 2 of these guys close to each other. Well, we're going to get an oxygen molecule, which is also going to be one of these diatomic molecules that we're talking about. Looks like this when we write it in a formula. We write O2 to signify that they're bonded together in units of 2. So the subscript 2 indicates that we have 2 of these. When we write out the bond in a structural formula, we're going to write 2 lines between them like this, where each corresponds to a bond, so to speak. Both of these atoms are going to have access to 2 more valence electrons because they're sharing with each other. So this guy to the left, it's pulling on the electrons of this guy to the right. The guy to the right is pulling on the electrons of the guy to the left. So as they're pulling on these, like the dogs playing tug of war, they reach a configuration where they actually have 8. So let's see, let's count the outermost valence electrons in this. 1, 2, 3, 4, 5, 6, 7, 8, yeah. 1, 2, 3, 4. Yeah, and we count that one as well. So we have 8 in total. Same goes for this guy. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have, both of these have 8 shared valence electrons. No, sorry, 8 valence electrons, but they are sharing in total of 4. And a covalent bond where we have 2 atoms that share 4 electrons between each other, that's called a double bond, which we write like this. And if you're using a Lewis structure, note the side-by-side placement of these electrons, and 4 of them in total. So write this down. 2 atoms share 4 electrons equals double bond. And we write that with an equal sign, or 2 lines, like that. Finally, the third type of covalent bond, there are no more types, that's the triple bond. And let's look, in order to illustrate that, we're going to look at nitrogen. So let's see, we have 1, 2, 3, 4, 5, 6, 7 protons, which should correspond to nitrogen. And how many valence electrons do we have for nitrogen? Well, look in your periodic table, and it will be in group 15, so it has 5 valence electrons, and this model here has 5 valence electrons, this Chadwick model that we're using. What happens if 2 of these atoms, these 2 nitrogen atoms, come close to each other? Well, we get something like this. A nitrogen molecule, again a diatomic molecule, as we can see by the subscript 2 here. We have a triple bond being formed, which we can indicate with 3 lines like that. If we're going to count their electrons now, let's see, both nitrogen atoms have access to 3 additional electrons. So we have in this part here, which is shared, we have 6 electrons, and then we're going to have 2 for this one guy and 2 for this. So this is going to be 8 in total. And if we look at the guy to the left, the atom to the left, it has 6 in a shared bond and 2 free electrons. So they both have reached 8 valence electrons. So they have reached a noble gas configuration. And I'd like you to write this down. A covalent bond where we have 6 valence electrons shared between 2 atoms, that's a triple bond. If we're going to write it using a Lewis structure, we can write something like this. Again, electrons, shared electrons side by side. And we can see that this nitrogen has 6 plus 2, so 8 valence electrons. This nitrogen has 6 plus 2, 8 valence electrons. Okay? We've also been distinguishing between pure covalent bonds when we've been looking at electronegativity values. And what do we mean with this? So, if we take the difference in electronegativity between 2 atoms that are bonded together, and that equals 0, then we call this a pure covalent bond. For example, the ones we've looked at. Fluorine, 2 fluorine atoms bonded together. If we take the difference in their electronegativity values, it's going to be 0. Same for oxygen and nitrogen. But we can also have this formed in other complex ways, like an octamer of sulfur, where they share their electrons in bonds this way. So we get 8 sulfur. So each unit of this molecule is going to consist of 8 sulfur atoms. So there's different ways of doing this than just forming diatomic compounds. Then we can talk about when we have non-polar covalent compounds or non-polar covalent bonds. When we take the difference in electronegativity and it's lower than 0.5, then it's a very small difference in electronegativity between the 2 compounds. And an example of that is the carbon atom and the hydrogen atom. If we look at the difference in electronegativity between these 2 atoms, it's going to be 0.4, which is lower than 0.5. Okay, so there's no real difference really in how hard they pull on electrons. So let's see what happens. Let's combine these 2, the carbon atom and the hydrogen atom, together. What would we get? So for carbon to acquire, well, 4 additional valence electrons, that's how we reach 8, right? It needs to share electrons, and how many? Well, it needs 4 additional ones. So we're gonna need 4 hydrogen atoms like this, because each hydrogen atom has 1 valence electron to share. So in order to fulfill the needs of carbon, we're gonna have them combining like this. So we have 4 hydrogen atoms per carbon atom. The hydrogen atoms, well, they will reach 2. They will acquire 2 electrons each. That corresponds to the structure of a noble gas, or the electron configuration of a noble gas. That's helium, right? So the hydrogen atoms are going to be pleased. They have achieved a noble gas configuration. The carbon, it has gained 4 additional valence electrons by sharing, and it's reached 8. Therefore, it's also reached a noble gas configuration. So we have pleased atoms forming a molecule here. And we formed a compound that's called methane. And we'll get into how to draw this in a structural formula later. But when we're going to write the formula for it, it's going to be CH4. So 1 carbon per unit and then 4 hydrogens per unit. In this case, the unit is a molecule. And this is the Lewis structure. We're putting electrons side by side to indicate that they are shared, like this. And which type of bonds have we formed here? Well, here we have a bond, shared electrons, here we have shared electrons, here we have shared electrons, and here we have shared electrons. That corresponds to 4 single bonds, because in each bond, or each shared, we have 2 electrons being shared between carbon and each hydrogen atom. So we're going to have 4 single bonds formed in this compound. Let's look what happens if we have a larger difference in electronegativity. For example, somewhere between 0.5 and 1.7. Remember, above 1.7 we have ionic compounds. So, if we compare hydrogen, remember 1 proton defines the element, and oxygen, 1, 2, 3, 4, 5, 6, 7, 8, so this defines the oxygen. Hydrogen is going to require 1 additional valence electron, so it will be like helium. It reaches a noble gas configuration. Oxygen has 6 valence electrons, require 2 more. So when these combine, we're going to get something like this. Here we have a different model of a water molecule than you've probably seen before, just to indicate where we have single bonds being formed and how they share their electrons between shells. So it's a model. We can look at this differently as well. We can also visualize the electrons shown by clouds. So, and we did this for the metallic bonding before, but bear with me. So some parts of this molecule are going to be more electron dense. And what I mean with that is, remember that oxygen has a much higher electronegativity than hydrogen. So oxygen is going to pull on the electrons much harder than the hydrogen atoms. So the electrons, not shown perfect in this model, but the electrons are going to be closer to the oxygen than the hydrogen. Oxygen also has free electron pairs, free valence electrons, as you can see up here. So we're going to get a structure where we have a half of this molecule is going to be way more electron dense, more tightly packed with electrons, and one part that's going to be less packed with electrons because oxygen is pulling them away. So this is going to be less electron dense. So more electron dense close to the oxygen atom and less electron dense close to the hydrogen atoms, because this guy is pulling harder on electrons. Then we get a difference here, right? We have one region which is more tightly packed with electrons and one region that is less tightly packed with electrons. Molecules that look like this are called polar molecules. So water is a polar molecule, for example. One side is going to be more negatively charged than the other. That's because we have slightly more electrons over here than we have over here. The other side is going to be more positively charged because we're pulling away electrons from here a little bit, so it's going to be more of a plus charge on this side because we're sort of losing our tug on the electrons a little bit. So we're not cancelling out the positive charge from the protons as well. And we have formed a polar molecule. When we have molecules with 2 poles like this, with different so-called partial charges, we have formed a dipole. These will give the molecules fairly interesting properties, as we will see when we're talking about intermolecular compounds and forces. Right, so to finish up, and we're going to build some molecules and discuss whether or not they are polar in class, but there's 2 things, two criteria that are required for a molecule to be dipole. First and foremost, we need to have polar covalent bonding. And remember, that's a difference in electronegativity somewhere between 0.5 and 1.7. And it has to have an asymmetrical shape. And what do I mean by that? Well, we'll get to it in class, but try to visualize how a carbon dioxide molecule would look for now. And I think that's it. Hope you've taken thorough notes, and I will see you guys soon.